Okay, I'm working 13.7, which is surface integrals, and going to be starting with number 5. So we're asked to find the surface integral over the surface S of x plus y plus z with respect to surface area, where S is the parallelogram with the parametric equations x equals u plus v, y equals u minus v, and z equals 1 plus 2u plus v. U is between 0 and 2. V is between 0 and 1. All right, so I'm going to convert the parametric equations over to the vector form r of uv. So my surface S can be drawn with this. So that means it can be drawn with this vector form of this surface. Okay. And we're trying to find the surface integral. Now this right here is a linear function, which means, scalar function, f of x, y, z. So I'm trying to find what this is. The surface integral over the surface S of a scalar function with respect to surface area. So if you go to the formulas that were provided to you in class, let me write the formula up here since it's the first time I'm doing one of these. Give me just a second here. All right, yeah, so I'll do it exactly the way I did it there. So what we're going to do is we're going to convert this into a double integral over the region D. Now D comes from our restrictions on our u and v, okay? That's going to give us our limits of integration. It will be our scalar function evaluated at the vector function. So we're going to take the vector components, the components x, y, and z, and we're going to replace them into the scalar function. Then we're going to multiply that times the magnitude of the cross product of the partial derivatives of r with respect to u and v, respectively. And then this will now be with respect to area. So this right here is this. And then this right here is just the function evaluated. So I'm going to need some stuff in order to do this problem. I'm going to need quite a few things. So let me get some partials here and then cross them, then take the magnitude, and then we should be ready to roll. So I'm going to take partial of r with respect to u is 1, 1, 2. Partial of r with respect to v is 1, negative 1, 1. And then I cross these, so r, partial of r with respect to u, cross with partial of r with respect to v. Let's see, we've got 1, take away negative 2, so 1 plus 2 is 3. So we've got 3 minus 3. 3, and then now let's do this one. So 1, take away 2, but then that's negative 1. But then it's the middle one, so I switch the sign so it's 1. And then here I've got negative 1, take away 1, which should be negative 2. So our cross product of the partials should be that vector. Before I get too far, I'm just going to double check it. Yep, okay. And now we need its magnitude. So the magnitude of this is going to be the square root of each of these squared and added together. So 9 plus 1 plus 4. That's going to be root 14. That's just a constant, so we got lucky. We're going to be able to pull that constant out of the double integral. So I was just about to erase that. I need it. I don't need this. I'll keep my restrictions. So this becomes double integral over d of Now, the scalar function, which was this one, replace the x with this, the y with this, the z with this. So it's just going to be u plus v, that's x, plus u minus v, that's y, plus 1 plus 2u plus v, times root 14 with respect to area. Let me clean up the inside of that there. And I'm also going to put my limits of integration on here. I'm going to go 0 to 2, 0 to 1. That means I'm going to have on the outside du and then on the inside dv. Let's see, u, 2u, 4u. V minus v cancels. So I just have a v and then a plus 1. So I get plus v plus 1. Root 14, I pull that out. And then d, like I said, v, d, u. And in an effort to save us time, I'm going to trust that you can do that and just give you the result. This should be 11 root 14. All right, that was pretty straightforward. They gave us the vector, the surface. They gave us the limits of integration. We were in business. All we had to do is just kind of evaluate the cross product, take its magnitude, plug everything in and go. So let's see where these start to get a little messy. Number 7, they give you, again, they give you the all the information you need, so I'm going to let you do that one. I'm going to do number 9. So 9 is different because they give you the surface integral they want you to evaluate. They want it to be x squared yz with respect to surface area. They say that S is part of the plane, z equals 1 plus 2x plus 3y. That lies above the rectangle 0, 3, 0, 2. So this is the definition here of S. So what we know is we have a plane here, right? Sitting here in three-dimensional space. If we look at the ground, this is on the ground 0, 3 to 0, 2. We're looking at the plane just above this, okay? So wherever the plane is, just that one little rectangle mapped into the plane, that's the surface we're integrating with respect to, okay? We're not trying to find the area, that was last section, but that's the surface of integration. So we need to find some vector function which will draw that. But we notice that this is some function. I can call it f. I think in the notes I call it, let me see, in the notes do I call it g? This is a special case. Yeah, I call it g. Yeah, so I call it g because we're calling this right here our scalar function f of x, y, z, so we don't want to use f twice. So g of x, y, right, is equal to square, I have no idea why I just put a square root there. And I just got a text message, so let me see what that's all about. This is just 1 plus 2x plus 3y. Let me just check my phone real quick. Software update. Okay, now, if we can write our surface S in terms of x and y, all right, if the z coordinate is in terms of x and y, then what we have is that the magnitude of the partial, right, the cross product that we do, these partials, here it'll be in terms of x and y instead of u and v, that this turns out to be with the formula 1 plus partial g, I'll say partial g with respect to x squared plus partial g with respect to y squared. So that should look very familiar from last section. So let me go ahead and put that in. Partial of g with respect to x, which is this, is 2, and then square it, so we get 4, plus partial of g with respect to y is 3, but then square it, so we get 9. So do we get root 14 again? We do. Okay, coincidence. So what we need to remember is this is a special case. What's happening here is that x is just x, y is just y, and z is the function of the two. So when I come up here and I'm trying to convert this over, double integral over d, d is going to be controlled by these, this is my restrictions on x and y. The scalar function evaluated on s means I'm just going to replace x with x, I'm going to replace y with y, and I'm going to replace z with this. So that becomes x squared times y times z, which is 1 plus 2x plus 3y. And then I have times this, which is this, so times root 14. I can pull that out. And then dA. All right, so please understand, this is the same formula from last time, with the exception that this computation right here is easier, and that when you plug into the scalar function, we're not plugging in functions of u and v, we're plugging in functions of x and y. It's just because the nature of the special case here. All right, so now this becomes, let's see, root 14. And then I can use my limits here, 0 to 3, 0 to 2. You can distribute this through if you want. X squared y plus 2x cubed y plus 3x squared y squared. So I distributed that through. I took my root 14 out, and then this is going to be dy dx. Let me just make sure I've got that all set up properly. X squared y, 2x cubed y, 3x squared y squared. 0 to, where are we? Y squared. 15. Okay, yeah, so again, I'll let you work this out. This is a double integral, pretty clean. This should turn out to be 171 root 14. All right, let's look at number 11. Although 10 looks kind of interesting. Let me try and set up 10 quickly. Okay, so for 10, you have a surface integral of, let's see, xz with respect to surface area. And S is the part of the plane 2x plus 2y plus z equals 4 that lies in the first octant. So if we're going to be in the first octant, we need to figure out where that plane comes in and cuts through. Probably it's going to be something like this. You know, we have like almost like a tetrahedron looking thing when that plane cuts through. So I'm going to try and just figure that out first. To do that, I let z be 0. If z is 0, then I get 2x plus 2y equals 4. That's x plus y equals 2. that's y equals negative x plus 2. So if I draw this in the xy plane on the ground, up 2, and then it's down 1 over 1, down 1 over 1, so it's going to hit here at 2 also. That's where my plane hits. So I'm just looking at the surface, the plane above that, right? And where does it hit the z? At 4? Hits here at 4, hits here at 2, hits here at 2. So this is my surface S. I can control that surface, or I can actually draw that surface pretty easily. You know, if I look at this down on the ground as a type 1 region, my x is between 0 and 2. My y here is between 0 and this line. That line is this, so negative x plus 2. And I should be okay to use a special case here because my z coordinate, I can solve this for z. Like that. And now my z is a function of 2 variables. So this gives me my special case. So I can use that shortcut. So when I go and I convert this into the double integral over d of what? F of x, y, z, I'm just going to remember that because this is a special case, x is just x, y is just y, and of course z is this. So when I go to rewrite this, x will just stay x. Z will turn into this, so negative 2x minus 2y plus 4. But then the next part is the square root, so this is the shortcut part, of 1 plus the partial of g with respect to x, which is negative 2 squared, so 4, plus the partial of g with respect to y, which is negative 2 squared, which is 4 again, and then dA. And where's my little cloth? There it is. And this becomes, let's see, double integral. Let's see, we can put the limits of integration in here, 0 to 2, and then 0 to negative x plus 2. What is that? Root, that's 8, 9. Hey, that's a 3. Let me pull the 3 out. 3. And then distribute through here, we get negative 2x squared minus 2xy plus 4x. And I'm going dy dx. I have to use that order because this was like a type 1 region. So we're looking at trying to evaluate this double integral. This is number 10. 3, 4, 8, minus 2. dy. Yes, that's all good. And then I'll let you work the rest of this out. This should equal at the end of it all 4. Maybe I have time for one more right now. I think 11 is similar to 10, except that you have to come up with the equation in the plane first. It's going to take a little more work. Let's look at number 13. I am recording, right? Yeah. Which one did I say I was going to do? 13? Surface integral x squared z squared ds, where s is the part of the cone, z squared equals x squared plus y squared. That lies between the planes z equals 1 and z equals, where's it, 3. All right, now let me get a picture of what's going on here. What does my S look like? Well, it's this cone, which looks like this. Actually goes the other direction too, like that. However, we're just looking at the surface that is cut off between z equals 1 and z equals 3. So if we imagine just coming through and slicing this, you know, raising up off the ground 1 unit, slicing it, we'd slice it here somewhere. Raise up to 3, we'd slice it here. This one's kind of easier to draw. This is just going to give us this surface, right, is what we're integrating over. So this is our S. So the question is, can we come up with some sort of representation of this surface? Well, because I'm only on the top part, I don't need to consider the bottom part. I can look at this as being the square root of x squared plus y squared. That's what z is. And in that case, z is a function of x and y. Also, when I look straight down on this, right, when I look from the top, the region on the ground, the xy, the region that my surface is casting a shadow onto is this region. You know what? Nope, that's not correct. Let me back that up. Why can I not keep that darn thing? Let me do it this way. Okay, so we have, if you look at this going to the ground like that, and I'll take this part out, then we get on the ground our region of integration is going to be a polar region. My question is, do we want to go get that now? I guess we could. Let's try and figure out where this hits the ground. So what we want to know is, you know, how wide this is, right? So I want to know when that cone hits the z equals 3. So when does this cone equal 3? So when does square root of x squared plus y squared equal 3? Well, you square both sides, you get x squared plus y squared equals 9. And so it's going to hit at a circle of radius 3. So that was correct for me to assume that this was 3. And then if I do the same thing, I say, where does it hit this plane z equals 1? I make a 1 here. Square both sides, I get 1. So this would be a circle of radius 1. So the inner piece is 1 here. All right, but let's get down to business here. This is just setting up like my restrictions in determining I'm going to go to polar at some point. I want to see if this is a special case. So can I convert this over? And we can see it is, right? Z is a function of x and y. So this is my g of xy. So just remember that x will be x here, y will be y, and z will be this, right? Z will be this. So this becomes a double integral over some region D, which is this, of x squared, so it's just x squared, times z squared. So z is actually this, and if I square it, I get x squared plus y squared. That's really nice. And then I need to come in and get this, this special piece right here, which is the square root of 1 plus the partial of g with respect to x. So taking the derivative of this root. We did that earlier in a different problem. It was this thing over square root of x squared plus y squared, but then we had to square it. And then we did the same thing on this one. It was y over square root of x squared plus y squared, and then we had to square it. And then we have dA. All right, now, when we did this earlier and squared it, I don't know if you remember, it turned into root 2. So I'm going to just write a root 2 on the outside. And then I have x squared times x squared plus y squared. I do realize I could distribute that through, but I'm not going to because I'm about to convert this to polar. Because I can't get restrictions that are nice on x and y. That's a good polar region. So converting now to polar, I know my theta is going to be between 0 and 2 pi. I know my r is going to be between 1 and 3. Be careful here, 1 and 3. And so this becomes root 2 integral 0 to 2 pi integral 1 to 3. Okay, x squared plus y squared in polar is r squared. And x squared is r cosine theta squared, which becomes r squared cosine squared theta times r squared, times an r that we have to insert because of polar. So I should have r to the 5th cosine squared theta dr d theta. And I got my root 2 out there. Just double check this. Root 2, 0 to 2 pi, 1 to 3, r to the 5th cosine squared. That's all good. Working that out. By the way, you could split this into two integrals and multiply them because r is isolated and theta, the function of theta is isolated, or just work it out normally. They're giving me something like 364 root 2 over 3 pi. All right, that's number 13. I'll do more of these later. Okay, I'm working 13.7. Number 19, we have this surface integral. Here's our surface S. We have a cylinder, radius 1, that comes out the x-axis. We're looking in the first octant and we're cutting it off between x is 0 and x is 3. So let's see. X equals 0 is the YZ plane, and our cylinder comes out this way, so it's going to do something like this, and then it's going to wrap around the back side, but we're only in the first octant. It's going to come down like this to x equals 3. Okay, we'll have something like this. Okay, see if that makes sense to you here. Cylinder, radius 1. 1, and this is x is 3. X equals 0 is the back side, but all we're interested in is this surface right here. Okay, this part of it is the S, and we're trying to find this surface integral. So when we look at this surface, right, we want to see how can we draw that surface. All right, so let me work on trying to come up with some parameterization of the surface. All right, it doesn't look like it's going to be an easy one to write where z is a function of x and y, or y is a function of x and z, because I can't solve this easily for one of those variables. So let me try and come up with this parameterization. We'll take care of all the other details afterward. So I want to draw the cylinder. It's this outside edge using the YZ plane to draw circles. So I'm looking at something like, since the radius is 1, I'm looking at something like cosine u, sine u. That should draw me unit circles because the radius here is 1. I only want my u, I only want to draw these quarter circles, okay? So I want my u to be bounded between 0 and pi over 2 instead of 2 pi, which would draw me all the way around. And then my x coordinate, I want to start at 0 and come out to 3, so I'm going to let this be v, and let v be between 0 and 3. And that should draw me what I need. Okay, now the next thing is to go ahead and find the cross product of this. So let me move my restrictions over here. U is between 0 and pi over 2. V is between 0 and 3. Now, when I do my partial with respect to u, partial of r with respect to u, I get 0. Okay, and then I get negative sine u, then I get cosine u. When I do the partial of r with respect to v, I get 1, 0, 0. Now remember, what I'm trying to do here is get this part of it, ds. And ds was the magnitude of the cross product of the partials, right? dA. Okay, so that's what I'm going for here. The cross product here, partial r with respect to u, cross the partial of r with respect to v, is going to be a vector. We'll cover this up here. We get zeros there. And cover this up, we get 0, and then we get negative cosine, or minus cosine u, but it's the middle one, so it's positive cosine u. And we cover this one up, we get 0, and then minus and negative, so it's going to be plus, so we get sine u. And then when I take the magnitude of that, it's the square root of this squared plus this squared plus this squared. These two squared and added together is a 1, so we just get 1. So we just get 1, which is really, really nice. So now we're ready to go ahead and do the surface integral. I'll do it over here. And I can go ahead and convert this over now to my restrictions here on u and v, which constitutes my d region here. So we get double integral. Let's go 0 to 3. 0 to pi over 2, and then I'm going to have this, which I need to plug in my component function, or the components of my surface. So the z is sine u, so I've got sine u, plus x squared, which is going to be v squared, and then y, which is cosine u, and then times this, which is this, that's a 1. So times 1, I'm not going to put it. And then dA is du dv or dv du. In this case, I'm going to go du dv. All right. So this is it. Now we just integrate that with respect to v first, and then with respect to u. Let me just tell you what the answer should be here. You should get a 12 here. Okay, that's it for that one. Let's take a look now at number 21. So now we're switching over to surface integrals over vector fields. So flux. Number 21 is the first example of this. And we have evaluate f dot ds across the vector field. They give you the field is, let's see, converting this over, we've got z e to the xy. We've got negative 3z e to the xy. And just do something, make sure I didn't do this one. Yeah, I did not do this one, okay. And then xy, like that. So there's our field, and then the region S is the parallelogram of exercise 5. So exercise 5, I did that earlier. It was this. R of uv is, let's see, u plus v, and then u minus v, and then z was 1 plus 2u plus v. Our restrictions here were that u is between 0 and 2, and v was between 0 and 1. Okay, so that's what we had from number 5. Now, I'm going to save myself some time. I'm not going to go through and do everything I have to do here because we already did it earlier. So I'm going to be using the formula that this is equal to double integral, and let me see, in the notes, oops, in the notes I'm referring to, that's good, formula, let's see, 1377, so we're going to go F dotted with R U cross R, partial R with respect to V dA. So I need to find the cross product of these partials, which we did in number 5. And let me just look that up real quick so I don't have to redo it. The cross product, when we did the cross product, let's see, I'll put it right here. When we take partial of R with respect to U and cross it with partial of R with respect to V, we should get the vector, we got the vector 3, 1, negative 2. You can check back in the video for number 5 that we did in fact get that. Now, here they say that they want the upward orientation for the parallelogram. So, you know, we have this parallelogram three-dimensionally, okay, whatever it looks like in three-dimensional space. That's our S. And we want our normal vectors, okay, to be pointed upward, okay? So we don't want them going kind of into the parallelogram and down. We want them to be coming out like this. So we want our cross products to make sure that they're coming up. And so you can tell when you look at this right here, if this is our cross product, notice that the Z component is negative, which means these are actually the ones that are pointed downward, okay? That's what that actually is, all right? This is what we have because of the negative component here. But we want them to be up. So what we're going to need to do in our formula is we're going to need to change the signs of this. We're going to have to take the negative of this, which will still be a normal vector, it just will point in the opposite direction. This is the one that we're going to use, okay? That's ours. So you have to pay attention to that subtle little detail there. And then at this point, we can start putting things together, but let's see, I'm going to use the F, which is this, dotted with this right here, but I also need to evaluate F on my surface. So I need to now set up, I think I'll do it right underneath this. What is, this is just separate work, because I'm trying to get these two parts. I've got this part, okay? Now I need F. That's really the field evaluated on the surface, like that, which is a vector. It is the vector, let's see, Z, which is this, 1 plus 2u plus v, e to the x times y. X times y, notice that's a difference of squares. When you multiply those, you get u squared minus v squared, comma, now this, negative 3z, so negative 3 times the z, all right, and then e to the same thing, e to the u squared minus v squared, and then the last part is x times y, which again is u squared minus v squared. All right, I've got to take that now and I've got to dot that with this. So now I think I'm ready to set up this double integral right here. So I have double integral over the region D. D are my restrictions on u and v. F evaluated at the surface, which is this. Okay. Okay, getting there, and then u squared minus v squared. I want to dot that with this vector, which is -3, -1, 2, and then dA. And hopefully, if we're lucky, the way they made the problem, things are going to get nice here. Let's see. So when I dot -3 times this, and then watch. When I do -3 times this, I get -3, 1 plus 2u plus v, e to the u squared minus v squared, plus, because it's a dot product, -1 times this makes that a +3, and then 1 plus 2u plus v, e to the u squared minus v squared, and then plus 2 times this, which is 2u squared minus v squared. All right, dA. So all of that. And notice that these two are opposite in sign, but they're exactly the same, so those go away. Gosh, we got real lucky there. So this equals the double integral, and then I'll go ahead and put the limits of integration on here now. Our restrictions are, let's see, 0 to 1 on v, and 0 to 2 on u. And then I've got the 2, I'll bring the 2 out here, and then I've got u squared minus v squared du dv. And that's it. That's a pretty straightforward integration here. And when you work through that, you should get 4. Okay. Let's take a look now at number 25. So we have vector field given here. Has the components x, -z, and y. That just looks really familiar. Okay, it's not. And then S is the part of the sphere in the first octant. S is the part of the sphere x squared plus y squared plus z squared equals 4 in the first octant. All right. And they want us to use orientation toward the origin. All right, well, first thing we need to realize is what we're working with here as far as the surface. So we're in the first octant, and we're looking at a part of the sphere, the surface of the sphere with radius 2. So the back side's like this. This curves over like this. And so we have this part of the sphere. Right, so we've cut out part of the sphere like that, kind of. So it's only the part in the first octant. And we're actually looking at this surface. So it's this curved surface on the outside here towards us here. Okay, and that's our S. Also, we want to keep in mind that the normals that we have, we don't want them pointing out. Okay, that we want them to point in. All right. So we're going to need a couple of things here. We need to find some parametric representation of the surface, and to kind of cut back on time, I'll just ask you to remember, well, which one am I doing? Number 25? Oh, okay, yeah, we can do this several ways.
I like the way the book does it because it uses one of our formulas. Now, generally speaking, we could not look at this surface as a function of two variables because it's not a function because it's the whole surface or the whole sphere. But if we're just looking in the first octant, just looking at the parts where z is positive, then we could take this if we wanted to and solve it for z and take the square root and only have to worry about the positive square root because we're not looking at negative z values. So this right here can be our surface and we can look at our surface as being a function of just two variables. Now we have this sheet with these surface integrals in the special cases. I'm looking at the top case. Now it says that our flux ds should equal the double integral over d of negative p times the partial of g with respect to x minus q times partial of g with respect to y plus r dA if our normals are pointing upward. But our normals are not pointing upward, our normals are pointing inward. So what happens is we change this to a positive, we change this to a positive, we change this to a negative. And then remembering that the P, Q, and the R here are just our components of our field, and then G is this, then all we have to do is compute that, this multiplication, these partials, and we're there. We do need to figure out what our restriction on D is, but we'll get that in a second. All right, so let's now set this up. Okay, this is going to be equal to the double integral over D of, okay, P here is X times the partial of G with respect to X. So the derivative of this with respect to X is 1 over 2 square roots of 4 minus x squared minus y squared times the derivative of this with respect to x on the inside, which is negative 2x. That's just chain rule. Plus q is negative z, times partial g with respect to y, which would be very similar to what we just got over here. It'll be times 1 over 2 square roots of 4 minus x squared minus y squared, but this time times negative 2y. Okay. And then we have minus r, which is y, dA. Now that doesn't look very pretty. I agree with that. I'm wondering if I should clean this up. Yeah, let's clean this up just a little bit. This will be, I don't need this, double integral over d, x and x here, and then these twos cancel. We get negative x squared over square root 4 minus x squared minus y squared. And then here, these cancel. We get negative y, right? But then times z. Remember, what is z? Well, this is z, right? That's z. So also notice the negative and the negative become plus. So really I'm going to have y times this, but this is the same as this, so these are going to cancel, right? When I plug this in right here, these cancel. So all I have here is just plus y. And then the last part is going to be minus y, dA. And these y's cancel. And we get double integral over d, negative x squared over square root 4 minus x squared minus y squared dA. That doesn't seem right, but let me see, which one am I doing? No? Okay, that's good. All right, so now at this point, I need to think about how I'm going to figure out what D is. Now remember that we were working with the surface here, which was this part of the sphere up here. My question is, how can we figure out a restriction on x and y? Right, this is our xy plane that would draw that surface. Remember, this is g of xy. And if you notice this down here, that's a great polar region, right? In two-dimensional xy, 2, that's a really, really nice polar region. So what I'm going to do is I'm going to convert this double integral over to polar, and I'm going to put some restrictions here. I'm going to put theta between, let's see, 0 and pi over 2. And I'm going to put my r restricted between 0 and 2. And remembering all my things that switch, right? X becomes, in this case, r cosine theta, and x squared plus y squared, and all that stuff is r squared. So this double integral is going to go, let's see, 0 to 2, 0 to pi over 2. And I can go either way, right? Doesn't matter. Negative x squared is going to be negative r squared cosine squared theta over, and then here, remember this, I can look at that as being negative x squared plus y squared. X squared plus y squared is r squared. So we get square root of 4 minus r squared. And then don't forget that we also get an r and then dr d theta. What I'll do is I'll switch these. So pi over 2 here and 2. And so we can start cleaning this up a little bit. I like the idea here of, let's put this here with this r, and well, let me write it down, then maybe you'll see what to do from there. So 0 to pi over 2, 0 to 2, and now r cubed, negative r cubed over square root of 4 minus r squared, and then dr up cosine times cosine squared theta dr d theta. That's just rearranging things. And notice the r's and the thetas are separated by multiplication, so I can turn this into two integrals and multiply them together. So this is integral from 0 to 2 of the r stuff, negative r cubed over square root 4 minus r squared dr, times integral from 0 to pi over 2 of cosine squared theta d theta. Okay, now I'm just debating on whether or not I want to actually go through and do this. Yeah, I think I will. I am going to pull this negative out. Maybe I'll leave it. Let's leave it. Okay, so on this integral right here, let me do this. I'm going to work this completely through. On that first integral, it's going to be, let me just look at this. How about being a little clever here? Rewriting it like this. And then I'm going to make a substitution here. U is equal to 4 minus r squared. The derivative of that is negative 2r dr, which means negative, I have a negative r up here. So let me just divide both sides by 2. So 1/2 du is negative r dr. So what I notice is negative r dr is going to become 1/2 du. 4 minus r squared is u. And then to figure out what r squared is going to become, just solve this for r squared. So move the r squared to the other side, subtract the u. R squared equals 4 minus u. So just that integral right there becomes, see, the 1/2 came out, 1/2 du. And then on the top, I have the r squared, which is 4 minus u. And on the bottom, we have the square root of u. And you can split that into two different problems. So 1/2 integral 4 over this root is the same as 4u to the 1/2. And then minus u over root u is u to the 1/2. Negative 1/2 here, sorry. And then du. All right, now we just do some antiderivatives. Add 1 to that, you get 1/2. Flip it 2, you get 8. So 1/2, this is 8 u to the 1/2. That's the antiderivative of this. Check it. 1/2 comes out, that's 4. Subtract 1, you get that. Antiderivative of this, so minus 2/3 u to the 3/2, just adding 1. And then we replace our u with what it was. So I'll do that on the next, I'll do that when I go back up here. Now, for this one, I'm going to look at that one. Just remember what u was here when we switch back. U was equal to 4 minus r squared. Okay. So for this integral, cosine squared, I'm going to rewrite that as 1/2 plus 1/2 cosine 2 theta. It's just a pre-cal identity there. And take the 1/2 out. And get 1 plus cosine 2 theta d theta. And then antiderivative of this, 1/2 theta. Antiderivative of that is plus 1/2 sine 2 theta. All right, so we should be in business here. I think we're ready. So we will now evaluate both of these integrals. This one is this, and why don't I just pass the 1/2 through here? 1/2 and 1/2. That'll be a what? A 4, and over here that'll be a 1/3. So I'm going to have 4 square roots of u. Okay, minus 1/3, 4 minus r squared to the 3/2, evaluated 0 to 2, times, now this one is 1/2 times theta plus 1/2 sine 2 theta, evaluated 0 to pi over 2. All right, so let's plug in 2 first. So we plug in 2 here. We get 2 squared is 4. We get 0 here. We get 0 here. So everything's 0. But then we get 0. And then we go minus. Now let's plug in 0. If we plug in 0, we get 4. Square root of 4 is 2. 2 times 4 is 8. So I'm going to get 8. Minus, let's see here. 0 here is 4. 4 square root, that's what that means. Square root of 4 is 2, but then cube it, that's 8. So I'm going to get minus 8/3. Then times, over here, when I plug in pi over 2, I get, let's see, 1/2 pi over 2 plus sine of, let's see, 2 times pi over 2 is pi. So sine of pi is 0. So that's gone, nothing. And then I go minus, and now when I plug in 0 here, get 0 and sine of 0, 0. So we just get zeros here. So it's looking like, at the end of the day here, we're having, let's see, 8/3. Let's get a common denominator here. Multiply top and bottom by 3, so you get 24/3 minus 8/3. Which is going to be 16/3, but it's going to be negative, so negative 16/3. And then over here, this looks like times pi over 4. And that doesn't look right. Let me see. Yeah, but it is. Okay, this 4, so I get negative 4 over 3 pi. Negative 4/3 pi. All right. That was interesting. All right, let's look at one last one here. Number 29. So for 29, I'm going to be doing a slightly different approach. In which case, I'm going to, okay, let me write down the problem first. Let me erase all this. All right, we have 29, our field, which is x, 2y, 3z. All right. And then the cube, we have S is the cube with vertices plus or minus 1, plus or minus 1, plus or minus 1. So we have actually all these different combinations of these points. So let's take a look here. Okay, this is our x, so if we do 1 and negative 1, okay, so let's imagine we have 1, 1, 1. We can have negative 1, 1, 1. We can have, let's see, 1, negative 1, 1. We can have 1, positive 1, negative 1. Let's see if we've got all the different combinations here. Negative, negative. We can have negative 1, positive 1, and negative 1, negative 1, negative 1. Oh my goodness. Let's see, 1, 2, 3, 4, 5, 6. See if I've got all these. Negative, negative. No, I could do 1, negative 1, negative 1. And I feel like I'm missing one. I know I am. Should have a total of 8, because it's a cube, right? So maybe it'd be easier just to do it this way, right? You got 1, 2, 3, 4, 5, 6, backside 7, 8. So somewhere in the backside of this, got that 8th point. Yeah, let's just do it this way. I kind of like it if we just draw it like this. Now, we know that the x, y, and z axes come out through here. Let's see. Punches through the center there, and then it comes out over here, punches through the center there, something like that. It's about as good as I think I'm going to get. So really the most important thing is to understand what each of these faces look like in terms of surfaces. So we're going to have, what, 6 surfaces, a total of 6 surfaces. So let's look at this front surface right here, S1. Let's just do that. What is that? S1, all right, has the equation that your x-coordinate is out 1, and then every other point lies in that plane that's parallel to the yz axis. So x is 1, and then we have restrictions, okay, which we could set up restrictions, all right? I'm not going to do that. Well, I'll do it just for this first one. Y is between negative 1 and 1. Z is between negative 1 and 1. All right, we could continue to do this. S2, let's let that be the top one. S2 is z equals 1, and then I can do restrictions. S3, let's let it be this one right here, this front face. That would be y equals 1. And then for S4, let's do this back side here, which would be x is negative 1. S5, let's let that be the bottom right here, S5, which would be z equals negative 1. And then finally S6, What are we missing? Y is -1. So those are the 6 surfaces. And we're trying to evaluate the flux. So let me do it here. Trying to figure out what the surface integral over S of F dot ds is, but there's an equivalent double integral of F dot n ds, where S is the surface area, right? And remember what the definition of this was, okay? The definition of this was RU cross RV and dA. That's what that was. But this is the magnitude of RU cross RV dA. Right? So there's a difference between those two. And this one, what's nice about this one is this right here, this vector is just the normal vector of the surface. And with all of these surfaces, we have very nice normal vectors. And they tell us in the problem, well, we assume because it's closed that our normals are going to go outward. So like for S1, notice that since this is just a flat sheet, the normal vector would come straight out, down the x-axis, out the x-axis. So for S1, the normal here, I'll say normal 1, will be equal to the vector, it's going out the positive direction of the x-axis, 1, 0, 0. I know that for sure. So that means that if I'm trying to find the flux on S1, I just need to take F and dot it with the normal of the first surface 1, ds, which would be double integral over the restriction, or over S of, well, what is the F, what is this dotted with 1, 0, 0? So I'm taking X, 2Y, 3Z, and I'm dotting it with 1, 0, 0, which just gives me X, S1. So I've got double integral over S1 of X ds. But on S1, what is X? X is 1. So this is just double integral over S1 of 1 ds. And that's just the surface area, right, of S1. And the surface area of S1, we know this is a square, right? Right, now be a little careful here because this goes between -1 and 1, -1 and 1. So the length of this is 2 and the length of that is 2, so the area of that is 4. So the surface area here is 4. Now that makes things a lot easier, right, than doing anything else. Let's try, okay, that's just one of them. Let's try and do S2. So for S2, I think what I'll do is I'll erase this one. Okay, so for S2, by the way, we're going to add up all these answers. So the flux over S2, F dot the normal over S2 ds. Okay, what's the normal vector of S2? Let's see here. S2 is z equals 1. This one points straight up like this. So the normal of S2 is 0, 0, 1, right? Straight up. It's basically k hat. And so this becomes the double integral over S2 of x, 2y, 3z, dotted with 0, 0, 1 ds. And that just gives you 3z. So we get double integral over S2 of 3z ds. But on S2, z is 1, so that's just going to become a 3 here. And then what we can do is we can just factor out the 3, and we get 3 double integral over S2 of ds, 1 ds, which is just the surface area. And again, we know the surface area of that is, they're the same for all of them. So this is going to be 12, 3 times 4, so 12 here. All right, let's do S3. Maybe I'll move a little quicker. S3 is coming out towards us this way. It's kind of hard to see it, but it's coming out this way. And so for S3, the normal vector of S3 is going to be 0, 1, 0. Let's see if we can move a little faster now. This is going to become S3. This is S3, or N3. This changes to 0, 1, 0. And when we dot that, we get 2y here. But y here on this one is 1, so we get a 1, but we pull the 2 out. And the surface area of S3 is 4, so we're going to get 8 here instead. So 8. So far we have 4 plus 12 plus 8. And let's go now and do something a little more interesting. How about S4? So S4 is this backside, and the normal vector sticking out of that points this direction, which is the vector negative 1, 0, 0. So let's see how that changes things. I hope you can tell what that is. This is coming out the backside, so that hits that face and goes out, away. Okay, so okay, so we're going over S4 here now. The normal of S4 is negative 1, 0, 0. And then when we plug in, when we dot this, we get negative x here. Negative x. Hold on just a second. Yes, ma'am.
Are you busy right now?
What do you got?
Well, I was going to take your class fall this semester.
All right, sorry about that, got distracted. Where was I? Yeah, so we get negative x here when we dot these together, but pay attention here. Notice that on S4, x is -1, right? X is -1, so when you change this, it'll become minus -1, that'll give you +1. We won't have a 2 out here anymore, so you'll get the surface area of S4, which again is 4. And I'll finish it up. For S5, the normal vector is pointing down, so that's the vector 0, 0, -1. And I believe if you work through all that again, you're going to get 12 again. And then if you work through the other one, you're going to get 8 again. So you should have this plus 4 plus 12 plus 8, which is, what is that? 24 and 24, 48 should be the flux for that one. So there you go. Notice I didn't use any shortcuts, any formulas. I use that other formula, which is very convenient if you know these normal vectors are always staying the same, right? So when you have flat surfaces, that works really, really good. All right, that's it for 13.7.